Today, we want to talk about another classic problem from the greatest hits album of Calculus 1. And this is the ladder sliding down a wall related rates problem. So here's the situation. A 10-foot ladder is sliding down a wall. The foot of the ladder is going to slide away from the wall at a constant half a foot per second. And we want to know how fast the top of the ladder is sliding down the wall at a certain point. So not everything is moving at a constant rate. The top of the ladder is not going to slide down at the same rate as the bottom of the ladder. The ladder is a fixed length. And so the base of the ladder is going to have to go, is going to be moving different distances when the top of the ladder slides down. As the top of the ladder slides down, the base of the ladder is going to start at 0 feet from the wall. And then the top of the ladder is going to start off at 10 feet. And then they're going to switch places. So we have to capture at some moment in time when this is happening. And so here are the two moments in time that we're looking at. When the foot of the ladder is 3 feet from the wall, and then when the foot of the ladder is 6 feet from the wall. So we need some variables to stand in for all these distances. So let's call this horizontal distance at the bottom X, because I'm super predictable like that. The horizontal stuff is X. And we'll call the vertical stuff Y. I'm sure there's some alternate universe where it's just normal to have these the other way around. And I'm sure of that because I've traveled to alternate universes and seen how they do math, and it's really weird. There was one place where not only was X the vertical one and Y the horizontal one, but left was positive. Up was still positive. So, I mean, you know. So what we're looking for is this is not a static situation. We know that the foot of the ladder is sliding away from the wall at half a foot per second. That's how X is changing with respect to time. So this foot of the ladder sliding away from the wall is the change of X with respect to time. And this is 0.5 feet per second. So we're given that rate. We're given dx dt. So in terms of symbols that we're using, dx dt is 0.5 feet per second. The question says, how fast is the top of the ladder falling down? So this is a question about the rate. We're looking for dy dt. So that's what we're looking for. And we want to find this at two different moments in time. One where the foot of the ladder is 3 feet from the wall, and the other when the foot of the ladder is 6 feet from the wall. Presumably we'll want to compare the different rates at which the top of the ladder is sliding down to see if it matches our intuition about what should be happening here. All right. So let's write down what we know. So we need a relationship between X and Y. And since I'm dealing with a right triangle, I can use the Pythagorean theorem. That's why this problem is much easier to do in Stormwind than it is in Orgrimmar, because in Orgrimmar, there are no buildings with right angles in them. I don't know how orc buildings stay together. Nothing is right angles. So you can still do the problem, but you wouldn't get to use the Pythagorean theorem. You'd have to use the generalized Pythagorean theorem, which is the law of cosines. So it's a little bit messier, but that's okay. We need a relationship between X and Y, and we can just use the Pythagorean theorem for that. X squared plus Y squared is equal to 10 squared. So this establishes a relationship between X and Y. It's the same one that we used yesterday in the cars driving towards the intersection problem. Here's some things that we know. We know that dy dt, since the top of the ladder is sliding down the wall, while dx dt is positive, dy dt should be negative because the distance from the top of the ladder to the floor should be decreasing. So that's something that we know going in. If we make our calculations and dy dt doesn't come out being negative, something has gone wrong. So we've used the first parts of our calculus knowledge, interpreting the derivative as a rate of change. Now we need to use some mechanical skills from the chain in the form of the chain rule and in the form of the chain rule. So here's a relationship between x and y. I need a relationship between dx dt and dy dt. So I need to take the derivative of this equation with respect to t. So I need to take the derivative with respect to t of everything in this equation. The derivative of x squared is 2x, but that's the derivative with respect to x. So the derivative of x squared is 2x, but that's with respect to x. The chain rule says multiply by the derivative of x with respect to t. And that's how we get to a derivative with respect to t. Similarly, the derivative of y squared is 2y, but that's the derivative with respect to y. We need the derivative with respect to t, so the chain rule says multiply by dy dt. On the other side of the equation, 10 squared, the 100, is a constant, and the derivative of a constant is equal to 0. So now we've gone through and taken the derivative with respect to t. 2x is the derivative with respect to x, so we have to multiply by dx dt to get a derivative with respect to t. Interpreting derivatives as rates of change and adding in the chain rule, putting those two things together. Two great tastes that taste great together. Just like Reese's peanut butter cups. Not a sponsored video. So some of these we have a value for x, we have a value for dx dt. We're looking for dy dt, but we don't have a value of y. But we have a relationship between x and y, and we want to know what's going on when the foot of the ladder is 3 feet from the wall. So we want to know what's going on when x is equal to 3. So when x equals 3, we get 3 squared plus y squared is equal to 10 squared. So y squared is 100 minus 9. So y squared is 91. So y is the square root of 91. Now we just have to put the 3 things that we know into the equation and solve for the 4th thing that we don't know. So we have 2 times x is 3. Dx dt is given at 0.5. Two y will be 2 times the square root of 91 times dy dt, which is what we're looking for. And all this is equal to 0. So I plugged in the 3 things that I know to find the 4th thing that I'm looking for. So when x is 3 feet when the foot of the ladder is 3 feet from the wall, the top of the ladder is square root of 91 feet from the floor. Square root of 91 is how much? 9.5 feet. Now we just need to solve for dy dt. So dy dt I'm going to put the 2, 3, and the 0.5 on the other side, and then I'll divide by 2 square roots of 91. So I'll have 2 times 3, oh, it'll be negative. 2 times 3 times 0.5 divided by 2 times the square root of 91. As we suspected, we knew that dy dt was going to be negative because the top of the ladder, the distance between the floor and the top of the ladder is decreasing. So the derivative should be negative. So we get 3 over 2 square roots of 91, negative 3 over 2 square root of 91. Feet per second. So that looks like a negative 0.157. This is what's going on. This is how fast the top of the ladder is sliding down the wall when the foot of the ladder is 3 feet from the wall. When x is 6 feet from the wall, we get 6 squared plus y squared is equal to 10 squared. So y squared is 100 minus 36. We get y equals 8. And then we'll put that into the same equation. We'll have 2 times x is 6 times 0.5 dx dt plus 2 times 8 times dy dt and so dy dt will be negative 2 times 6 times a 0.5 divided by 2 times 8. So we'll get 3/8. So when the foot of the ladder is further away from the wall, we can see that the top of the ladder is sliding down faster, even though the foot of the ladder is moving away at a constant rate. Any questions?
Yeah, so first, a quick one. Back to the top, when we have x equal 3, then we have 3 squared plus y squared equal 10 squared. Then we go down to, we have 2 multiplied with 3. So the 3 is the x, correct?
Yeah.
And then where, yes. Where is this 0.5 coming in? Why do we need that there?
Where else do we have a 0.5?
How come we need to put it right there? You know?
In this equation, I have 2x and then dx dt.
Okay.
I have a value for dx dt, so we plug that, the 0.5 in.
Oh, dxdt, got it. Wow, thanks. And then on the right, we have 2 plus 2 square root of 91. That is the y value, correct?
Right, because it's 2 times y times dy dt. So y is the square root of 91.
Oh, wow. Okay. Thanks, Professor. It's clear now. I will review that again. Thanks.
Any other questions? All right. How's everybody okay? Everybody looks stunned because like nobody is moving. Oh wait, that's because you all just have pictures. Never mind. You look less stunned now. I'm just kidding. Most of you just looks like names. I have to wonder if how much students like the idea behind online class. I know the concept, you know, especially with me recording videos, I record the video, then I post it. I look at the number of students in class, I subtract the number of students who are attending the meeting, and then I subtract the number of students that are watching the videos, and I still have a positive number. So it makes me wonder, am I doing too much? Should I just be linking to some other videos that people are watching? Because there's been videos about this ladder sliding down a wall. They got to be all over YouTube. Anyway, just wondering. It's hard to tell because I don't see what's going on. Let's take another a look at another classic problem. This is going to be the plane flying overhead, and we're going to throw an angle into things. So trig functions have arrived on the scene. So this is going to be another classic problem of first semester calculus. All right, so here we got a plane flying overhead. Next semester, there are going to be some in-person options. This means commuting, by the way. I'm wondering if your willingness to commute is a function of, I think the first thing I would look at is a function of your age. Or maybe I should set it up as a function of your total time spent commuting. Because I think people that haven't commuted a lot in their lives are going to be more willing to say, yeah, I'll go back to being in person. But people that have had like 45-minute commutes for multiple years are going to be like, oh, no. Anyway, what are we talking about? A plane flies overhead. So what's going to happen is that the camera is going to be locked onto the plane. So as the plane flies overhead, the camera is going to have to rotate to keep it in view. So here we're going to set up a relationship between the distance, the horizontal distance from the camera to the plane, and the angle that the camera makes with the ground. So we got to come up with some values. Let's have the plane be flying at a fixed altitude. We could do this problem with the plane flying at a non-fixed altitude, but let's start with the easier one. Just like in physics, we could do the problems where we don't ignore friction and air resistance. But when we're starting out, let's ignore friction and air resistance. I guess those are kind of the same thing, huh? To make the problems simpler, and then add in the complicated stuff later. So let's suppose that the plane is flying at a fixed height of, let's say, 4. Let's go with kilometers. So we got this plane flying at 4 kilometers. We at a constant altitude of 4 kilometers, and we got a camera rotating with the plane. So here are the things that are going to be changing. One thing that's going to be changing is the angle theta. So the angle theta is going to have to rotate as the plane flies overhead. The other thing that's going to be changing, since the plane is flying towards the camera, I'm going to need to come up with a variable for the horizontal distance from the camera to the plane. The other thing I could be keeping track of is how far the camera is from the plane. So this kind of angled distance, because that's going to be shrinking as the plane flies closer to the camera. But since the plane is flying level, it makes more sense to set up our variable as the horizontal distance from the camera to the plane. That way, the speed at which the plane is flying can be expressed as a derivative, dx dt. Let's suppose that the plane is flying at a constant 300 kilometers per hour. So I left a suspicious space after the equal sign and before I started writing 300. And what needs to go in that space? And why do we need something in that space? Think about the situation. The plane is flying closer to the camera, as indicated by the arrow. It's hard to see which way the plane is going because it's so far away. It's just a tiny dot on the paper. But the plane is flying closer to the camera. So this distance, the horizontal distance from the camera to the plane, is decreasing. So dx dt, that rate of change, should be negative. Now what's happening is that the camera has to rotate to keep the plane in view. So there's some kind of rotation going on. D theta dt. And that is the thing that we'll be looking for. So we might have a question like, how fast does the camera have to rotate? Then we'll need to pick a fixed point in time when the horizontal distance from the plane to the camera is, and then we pick a value for x, or an angle for theta. So we might see something like, how fast is the camera rotating? That is, what is d theta dt? And then we have to pick at some point in time. like when theta is pi over 6 radians or 30 degrees. And then we could look at it at some later time. How fast is it rotating when at 60 degrees? Now, at this point, we can just list one point in time, list a point in time with one value of theta or x, because there's a relationship between x and theta. In this case, if we look at theta, x is adjacent to the theta. We have a right triangle. X is adjacent to the theta. I don't have any expression for the radius. That's changing anyway. But we did say that the plane was flying at a constant 4 kilometers. So 4 kilometers is opposite theta. X is adjacent to theta. So let's say that the tangent of theta is opposite over adjacent. So here's a relationship between theta and x. So when I say when theta is pi over 6 radians, we can figure out what the horizontal distance x is. And when theta is pi over 3 radians, we can once again figure out what x is. Moreover, we have a relationship between the two quantities. We have a relationship between the two rates, dx dt and d theta dt. Any questions? All right. So we're going to do the same thing that we did before. We're going to take the derivatives. We're going to have to use chain rules. So let's do that. I'm going to rewrite 4 over x because I'm taking derivatives. I want to write powers of x if I can. So I'm going to rewrite tangent of theta equals 4 over x as tangent theta is 4x to the negative 1. And just like before, we're going to take the derivative with respect to time first, we'll have to take the derivative of tangent theta with respect to theta, then use the chain rule and multiply by the derivative of theta with respect to time. So the derivative of tangent is secant squared theta. Then the chain rule says multiply by the derivative of theta with respect to time. This is equal to the derivative of 4x to the negative 1. So I'll have negative 4x to the negative 2, and then we'll have to multiply by the derivative of x with respect to theta. Now we just have to calculate. Now we have 4 things in our equation: theta, d theta dt, x, and dx dt. We're given that dx dt is negative 300 kilometers per hour. We're told that we want to know what's going on when theta is pi over 6 radians. So we'll have to use that to figure out what x is equal to. So when theta is equal to pi over 6, we have the tangent of theta is equal to 4 over x. So we need to know what the tangent of pi over 6 is. So what's the tangent of pi over 6? So if we can't remember, we can ask our calculator what the tangent of pi over 6 is. And it's 0.577. If we want the exact value, we just have to remember that tangent of pi over 6 is √3 over 3. So imagine your 30-60 right triangle and find the opposite over the adjacent. So tangent of pi over 6 is √3 over 3. 4, and this is equal to 4 over x. So x over 4 is 3 over root 3. So I'll multiply by 4. We should note that 3 divided by root 3 is equal to root 3. Because if I have x squared over x, we just get x. So 3 over root 3 is root 3. Multiply both sides by 4. X is equal to 4 root 3. Now I just need to plug all this stuff into our equation. So I have the secant squared of theta, which was pi over 6. D theta dt is what we're looking for. And this will equal -4 times x, which we calculated to be 4 square roots of 3 squared. And dx dt is how fast the plane is flying, -300 kilometers per hour. So we're just plugging in the three things that we know, 2 given, 1 calculated, and solving for the fourth thing. Some things that we want to notice about this. We know that when theta is 30 degrees, the d theta dt should be positive because the angle should be increasing as the plane gets closer. And we can see that that's what's happening. Secant squared of pi over 6 is going to be positive, and these two negatives are going to cancel out. So it looks like we're good there. We just need to calculate d theta dt. This will be how fast the angle of the camera is changing in radians per hour, because the time that we're using here, that 300 introduced the time, and that's going to be in hours. So we'll have to work out what this number is. So we might have to remember what secant squared of pi over 6 is. Secant is the cosine. Cosine of 30 is root 3 over 2. So secant is going to be 2 over root 3. So we're going to have to sort out what that number is. Then we're going to have to think, before we calculate for pi over 3, is d theta dt going to be greater or less when we go from pi, when we get to pi over 3 radians? Is the camera have to rotate? Will the camera have to rotate faster or slower? We should decide what should happen and then see if our calculation matches our intuition. Any questions?
Yes, Professor Leach, but this one is very, very complicated. On the right, when we have theta equal pi over 6, and
Yeah.
then we have tangent pi over 6 equal 4 over x. Then the bottom, how do you get square root of 3 divided by 3?
Tangent of pi over 6 is root 3 over 3.
Oh, so that's how you come out with that. Okay.
Yep.
And then x over 4 equal 3 over square root of 3.
Uh-huh.
Oh, right. I got it. And I got that part. How do you, on the bottom, where are those coming from? X square root
Just here, I'm just explaining why 3 divided by the square root of 3 is equal to the square root of 3.
Oh.
Because the square root of 3 is the square root of 3 squared. So if I divide the square root of 3 squared by the square root of 3, we end up with the square root of 3.
Right. Another one on the left, we have secant squared theta multiply d data over dt equal negative 4x to the power negative 2. And then we move to the bottom. We see a negative 4. And then where that negative 2 power go, you know?
Oh, it should be to the -2.
Ah, okay, that makes sense now. That's what I thought. Okay, I will review a note again. Thanks, Professor Lynch.
Cool. I was originally going to move the 4√3 squared to the bottom because of the negative exponent, but then I just started writing it where it was and then forgot to keep the negative. So good catch. 10 points for you, minus 1,000 points for everybody else. I'm just kidding. It's minus 1,000,000 points for everybody else. That's a loss of so many points. Next semester, y'all going to be back in algebra class. I'm just kidding. That's not how it works. 1,000,000 points will put you all the way back in arithmetic. I'm just kidding. I don't like using the rule where if your character gets killed, you lose experience points, and that might cost you a whole level. That's a little bit more hardcore than I like my video games to be. I know that technically this is not a video game, but isn't it really? Isn't this it? You have to do it on your computer. I need to institute achievements. Achievement unlocked. Throw in some cutscenes and stuff like that. I've actually never played Minecraft, so I don't know. Do you lose? I don't know. Do you get killed in Minecraft? I don't know anything about Minecraft except that you build stuff. It's like video game Legos. Oh, see, that's hardcore. You're building stuff and then your character dies and then everything is just gone. Brutal. My favorite was watching World of Warcraft players complain about having to have their ghost run back to their corpse so that they could revive. And you could just tell which World of Warcraft players had never played any like imported those hardcore Korean MMOs where that happened. You die and then any experience point, you just lose that. And it could be you lose levels. And it's just like hardcore. So, all right. So your job is to work out what this number is, and then do the same thing for pi over 3 radians. Before you calculate for pi over 3 radians, think about what should happen to the value of d theta dt. Is it going to be bigger? Or is it going to be greater or less than the d theta dt at pi over 6 radians? That is the camera rotating faster or slower at pi over 3 radians than it was at pi over 6? So that's what you want to do to finish out this problem. You could probably tell that I was not going to be answering that question because I like to build in cliffhangers, especially on a Thursday. And also I was kind of running out of space down here at the bottom. I wouldn't be able to fit it. Also, I didn't have a lot of faith in my ability to actually make this calculation on camera. All right, so that's going to do it for this week. I'll see y'all on Monday. Everybody have a good weekend, and thanks for playing.